So this video is a tutorial that will walk you through how to modify labs so they are more inquiry based and they resemble the 5E instructional model or also in alignment with Madeline Hunter. There will be some documents that you will need to refer to from Blackboard, but I will tell you when you need to use those. So let's get started. So the first thing we're going to do is we're going to analyze a lesson to see how inquiry-based it is. So online, you will need to find in the learning unit that goes with this presentation, the lab that is entitled Rusty Nails. So if you will open up that lab now, we will go through the analyzing process. Okay, hopefully you have that lab open, or maybe you've printed it out and you have it in front of you. This week there's also an article that you will go through and read, and this inquiry analysis tool is explained in that article, but we're going to go ahead and jump in and use this. So as you look at this, you should already notice that it's aligned to the essential features of inquiry that we've been discussing in week 1 and week 2. So remember, the essential features of inquiry are: 1, does the material engage learners in a specifically scientific-oriented question? 2, are learners asked to give priority to evidence? In other words, does the material tell them what information to collect, what data to collect, what evidence to collect? Third essential feature is that learners are encouraged to formulate explanations from their evidence. Fourth, learners are asked to evaluate their explanations in light of alternative explanations. And then the fifth essential feature is that learners are expected to communicate and justify their proposed explanations. So as we go through this, what I'd like for you to do right now is just to look at the lesson, and I want you to analyze this lesson in terms of how well does the material meet the essential features of inquiry. For a lesson or a lab or an activity to be inquiry-based, it must have at least one or all of the features present. Of course, the more that we have present, the more inquiry-based it is. So I'm going to give you a few moments right now to go through and kind of check and base your markings off of the lab. Okay, hopefully you had enough time to go through all of these questions. So let's walk through it. So what did you think? In terms of essential feature 1, does the lab have questions that guide it? And then do students have the opportunity to ask more questions, or do they generate their own questions? And are the questions that are given to the students, are they relevant not only for the students but for this lab? So hopefully with this first essential feature of inquiry, you said no to all of these features. So no, this lab as it's written right now does not engage learners in a scientifically oriented question. In fact, there's no question at all. So if a teacher were just to follow this right here, they wouldn't even know what they were doing, except they could figure out that they were putting nails into salt water and fresh water, and it has to do something with rusting. Do questions guide the lab? No, there's no questions in here that are given to the students, nor through the instructional procedure, nor are there any discussion questions at the end. And so we really can't say if the questions are relevant to students because there are none. In terms of ask learners to give priority to evidence, it tells them on here to record, check for rust daily from 7 a.m. to 8 a.m. Good Lord, they're going to be up early. Record picture and written evidence. So it tells them to record a picture and written evidence, but what evidence are they collecting? Are they looking for something specifically? So in terms of this, I would almost see no for this one because there's nothing that it's telling them what to collect except written picture and written evidence. But what written evidence? Essential feature number 3, encourage learners to formulate explanations from evidence. Hopefully you put no for all of this as well, because again, they're not encouraged to provide any explanation. They're not asked to generate any explanations from their evidence, and they're not asked to explain their reasoning. 4, compel learners to evaluate their explanations in light. Again, no, there's nothing. This is just a list of procedures. Students aren't asked to do anything. And even number 5 should be no. So you really should have marked this no all the way across. So while this might be a great activity for students to engage in, as it's written right now, it's just an activity with no purpose, nothing. And in fact, ladies and gentlemen, when you look through, because I did in just a second, I'm gonna walk you through how I would modify this lab. I did try and find the Virginia Standards of Learning that would go specifically with this. So rusting nails would fall under a chemical change because you have if you remember from class last night, the lesson that you analyzed called changes, if you get a new substance form or what chemists call a precipitate that falls out of a liquid, so it wasn't there before, but it seems to magically appear, that's a chemical change. So rust, the process of rusting, when metal oxidizes, is a chemical change because eventually that metal will completely break down and it changes to that rusty material, and we can't get that metal back once we get that rust. So in of itself right here, there's no inquiry in this. And I couldn't find any standards of learning that would match for this activity. And I say that because as you're getting ready to plan your lessons for the curriculum that your school division will give you, and they'll probably provide you with a list of objectives, if not a complete curriculum guide. So I do know that Virginia Beach City Public Schools does have a complete curriculum guide. I'm not sure about Chesapeake. I know they provide teachers and students with science textbooks, and so therefore the teachers have manuals. But those science textbooks, remember, cover far more than the Virginia standards teach. So you may not use every chapter in the textbook, and you may not even use the entire chapter. You may only use 2 or 3 pages to hit that standard of learning. But school division should provide you with the standards of learning. And most of the times what they've done is they've taken the curriculum framework and given it to you verbatim. So you want to make sure that whatever activities or investigations that you are engaging the students in, they are actually aligned to what you're teaching. So this would be an activity, while worthwhile for kids to see, because it's an example of chemical changes. And that's where I could, I guess, tie it in to look at chemical changes, but kids would not be responsible for knowing the process of oxidation, knowing that word. But that would be the only place that I could see where this activity would fit. And again, this is not an experiment, although we can infer it's an experiment because you are testing salt water and fresh water. But it doesn't even say to the students, this is an experiment. And again, as I walk through how I would modify this, the questions that I asked myself, there's a lot more questions that I have with this activity. So hopefully you can see how this tool is really helpful for you to be able to say, is this an inquiry-based activity based off the essential features of inquiry? Again, one or all of the features would mean it's inquiry-based. Less features means it's less inquiry-based, but it's still inquiry-based. Okay, so how would I modify this? Because this is your task this week. On Blackboard, you actually have 2 sample activities that you can pick. So interest-based choice, I would kind of go through each activity and pick which one you lean more towards. So again, by giving you choices, I am differentiating the product that you are producing for me to show your understanding by interest. I'm giving you a choice. Okay, so Dr. Flanagan's going to walk through this. How would I modify this? And I'm going to kind of give you the questions that as I look at things, as I look at activities, I ask myself, because I always try and put myself in that child and think about what do they know? What are they bringing to that lab experience? All right, so with this, I'm going to look just at this lab as it is right now with the steps, right? Yes, we know it's not inquiry based, but we're going to turn it into an inquiry based thing that's going to be fabulous. Okay, so as I look at this, I understand this lab, this activity is based off wanting kids to see changes. And specifically, they want them to see chemical changes as it pertains to metals. All right. And so what they've done is they've already manipulated the variables. So they've given the students the variables manipulated. So when we talk about the independent variable, that's what I, as the researcher, am choosing to vary. And so if I look at step 2, I can clearly see the variable that's being varied is the type of water that the nail actually will go into. So we have fresh water and we have salt water. All right, so that's my independent variable. And then as I read through the rest of it, my observations that I'm going to collect, the changes that I see, are actually my dependent variable. And so it's kind of inferred. It's not really clear. So again, with this activity as it is right now, I'm not sure kids would pick up on those independent and dependent variables because it's not clearly articulated. So kids aren't learning those skills as they're just going through this activity. So just know that we have to be explicit with kids because identifying variables in an experiment is very, very challenging for students. Even adults have trouble with identifying them. So as I look at this first piece and I'm thinking about what we talked about last night with Madeline Hunter and the 5E model, I know the very first piece that I want to do is engage the students into something. And so my questions that I have when I look at this is, have students even seen rust? Like kids today aren't going outside very often. So have they seen a bike rusting? Have they seen metal rusting? Have they even paid attention to that? So if they haven't, then I probably need to show them a picture so we are all clear on what it is that rust looks like. And so in my mind, a great strategy to use is one called see, think, and wonder. In fact, your picture of the day that you did last week sort of goes along with that. Remember, we modified that see, think, wonder, right? You saw the little kid, the baby with the bubble, right? And I asked you to tell me, what did you observe? What did you see? And then as you were looking at the picture, what were you thinking, right? So what inferences were you drawing? And then what were you wondering about? So see, think, wonder would be a great place to start with this. So that's what I would actually do with the engage. I just went out online and I found a picture that I thought would be kind of cool. Again, the grosser the picture, the weirder the picture, the better the picture. So as students, I could lead them through see, think, wonder. And at the end of it, once we had a chance to go through and share, what do you see? So great observations, thinking, oh, those are great inferences that you're making. And then wonderings, I could actually, we could go through that and list that on the board. And those questions could be used later for further investigations if I had time. So again, see, think, wonder would be a great place to start. This is where, of course, I would introduce kids and I would say, this is rust. And so we're going to be actually doing an activity with rusting and looking at how we can cause objects to rust. So the explore and that input that I would do next is I want to have kids see what happens when I put nails into water, fresh water. So look, kids don't know what happens when nails go into water. They've never seen it. Most of them haven't. I'm going to make that assumption that they haven't seen it. And so instead of giving them two variables right off the bat, I'm going to start with just one. And we're going to do sort of a descriptive investigation, right? This is research. We're going to research and investigate what happens when we put a steel or a nail into water. And so I'm not even gonna tell them, you're gonna watch this rust, right? The purpose I'm doing is I want them to see that rusting process. So I'm gonna let them set it up. They're gonna make observations of the nail before it goes in the water. And I'm gonna have them do observations after 2 days or 3 days. And so I may do this right before the unit on chemical change, just so that we can pull this out, right? But I'm having kids make observations before and then after. Why? It's a great opportunity to write a compare and contrast paragraph. And I want them to have a clear understanding of what the physical properties of that nail before it actually begins. And so then once they've seen them and they get back to what you see right here, we can clearly see there's rust happening on the nails, right? How cool is that? Then we'll actually get into the explain, right? And so this is where I'm going to go over rusting as a chemical process, a chemical change piece. I could use this where I introduce chemical change. We could do just like we did last night in class with the Freyer model of vocabulary. I could introduce the definition of chemical change, and they could put rusting down as an example. They could put a picture of a rusty nail, which would help them trigger it. If I wanted to do the elephant's toothpaste, again, at this point, I could, to show them another example of a chemical change where they actually felt the temperature change, just like we talked last night. So that could be a whole nother activity piece, right? This could, in of itself, this explain piece could take 20 minutes of class. So let me back up here for a second. This anticipatory set and engage piece could take about 5 to 10 minutes of my first day when I did this. And then I could have them set it up, the explore. So the engage and explore could all be within 20 minutes or 25, 30 minutes, depending on the time that I had. If I was doing this for middle school, then I could add the explain piece once we had the data collected, and that could be my next lesson. My point in saying that to you all is, remember, a lesson doesn't just happen all the time in 20 minutes or 30 minutes or 50 minutes, although 50 minutes gives me a lot more time to get through a complete lesson. But in elementary, typically you'll have 25 minutes for science in the lower grades, and you'll have 35 minutes for science in the upper grades. So that's not a lot of time once you get out the materials and you're asking kids questions and things like that. So again, you're going to do this 5E piece probably in chunks along a couple of days. So we've got our explain piece. All right, so I could move on to something else at this point and go to a different topic in my curriculum, but I know that what's a great piece is to have kids design an investigation to test something out. So one of the things that I want to do here is to use this as an opportunity to extend it. So remember, with this one, they've only seen fresh water. So now what I want to do is I want to guide my students to come up with their own investigation question. Of course, ladies and gentlemen, I know where we need to go as the teacher. And so I know where they're going to get, but I'm making the students feel like they have ownership by giving them the process. Now, I haven't modeled this 4-question strategy for you in class. I hope to get to it next week with our one of our investigations that we're going to do. That again, I way overplan, so I didn't think we'd get to it last night. But the 4-question strategy is just a brainstorming tool that you as the teacher can use to guide students to design their own testable question. And so essentially, you go through and you ask them 4 questions. The first question is, what happens or what happened when we put the nail into the water? What did you observe? So students would say they saw that it rusted over time. Great. And if that's the only response, that's perfect. The second question is, what materials do you need to use if you're designing, investigating a question on blank? And again, I'm going to give you these questions next week, so don't labor over this right now. This is more walking through the design process. So I would actually have them do the 4-question strategy. Second piece is, what materials do you need? So now that the students have put a nail in water and they've seen that if it sits in water, it actually rusts over time, and that's a chemical change, they're ready to say that if we're going to design an investigation on rusting nails, I need a liquid, I need a cup, I need a nail, and I need time for that nail to sit. So those are the materials or the conditions they need. Third question is, okay, if I change, what could I change about my materials that might affect how that nail rusts? So liquids, what could I change about the liquids that might affect how the nail rusts? Well, what if I use a different type of liquid? So we use water. What if I use soda? What if I use salt water? What if I use seltzer water? What if I used milk? I could also change the nail. So I could change it from a steel nail to a galvanized nail, or a different type of nail. I probably am not going to manipulate the time that it sits, because that's just, I could manipulate where it sits. I could, in this activity it said to put it away from the shade or sunlight. So I could put it in the sunlight, because maybe sunlight's a factor that speeds it up. Okay. Once we pick what we're going to change, I would probably guide the students again to change the type of liquid. And I could do salt water. Then the fourth question is, what are you going to observe or measure that will tell you changing the type of liquid makes a difference in how the nail rusts? Well, I'm going to look at the time that it takes for the nail to rust. So in water, just regular water out of the tap, I saw that it started rusting within 3 days. And so 3 days, and maybe I could change the number of days. So I'm going to change the time that it sits in the water. And so then my investigation question that the students write comes from 3 and 4, because question 3 is where you brainstorm all of your independent variables. Question 4 is your dependent variable. And again, I'm going to go through this next week in class. I know this is probably not the best medium to do this, but the question that ultimately we would come up with is, I'm investigating the effects of changing the type of liquid on how many days it takes rust to form. Boom. There's the investigation question that kids have brainstormed and generated, but I've guided them. So this is how you can take a very structured, as we have it right now, right? So this is a confirmation structured lab, and boom, change it into a guided lab by just asking those 4 questions. Again, I'm going to model this for you next week so that you can see it. But that's how I would do it, and I would do it under this extend piece guided practice. All right. And then, of course, assessment at the end. I could assess students at some point on, looking at, chemical changes. I could give them pictures of examples of physical and chemical change, and they would have to sort them into those groups. And so that might be my assessment piece. All right. So hopefully you tracked with me on that. So again, how I changed it is I start with an anticipatory set where the students do a see, think, wonder, and they start to kind of grapple with this whole idea of, wow, this metal right here has changed, and look how it's changed, and it's got this orange color, and I see where the metal seems to be splitting right there. It's opening up, right? So they've asked their questions, they've told me their observations, they've made their inferences. The next piece that I do is I let kids experience what rusting looks like over time, and so we see it, that it's sitting out for 2 days. It's just water. I'm not changing multiple conditions at this point. I'm just allowing them to see the water. And then, of course, I do direct teaching. Maybe we see a video. Maybe I do the elephant's toothpaste. I do the Freyer model, so kids have a clear definition of that, of chemical change versus physical change, which I've probably done it another day or 2 before. And then, of course, then we move into designing our own investigation where they have a chance to come up with the question and so forth. And that is how I would modify that lab. In this second portion of the learning unit this week, I want to walk you through how I take an SOL, which is a standard of learning, and design a lesson around that standard. All right, so what you will need for this portion of our discussion is you will need the force, motion, and energy SOL document that's in Blackboard. So if you will get that out and have it ready. All right, So the state has written standards of learning. Those standards of learning you'll see in the bold, K through point 2. If you look at the first page of your document, the student will investigate and understand that pushes and pulls affect the motion of objects. Key ideas include, and they've got A, B, C. That is the actual standard. What you see below that is what comes from the curriculum framework. And the curriculum framework unpacks that standard to give you how deep you go in your instruction and how wide you go in your instruction. And what I mean by wide is how many topics you cover. You can see that I've given you the kindergarten standard, the first grade standard, and the second grade standard. This lesson plan that I'm developing comes specifically from the first grade. But I gave you the kindergarten and the second grade standard because I want you to see the vertical build of content. This is really critically important because if a teacher in kindergarten fails to introduce his students to this fundamental key basic idea of pushes and pulls, then your first grade students will be lost. And so you will have to go back and introduce pushes and pulls. So this is why we tell teachers you must be teaching what's in your grade level because it's critically important that students have experiences with this. So if you would, just take for a moment and look at the first grade standard for force, motion, and energy, where we're specifically looking at investigating and understanding that objects can move in different ways. Take a moment and just sort of peruse this page only. Okay. Let me just describe for you how this curriculum framework has been designed. So like I mentioned just a minute ago, they took the standard and they wanted to say, what does it mean when we say objects have straight, circular, spinning, and back and forth motions? So what specifically do students need to know and be able to do? Notice they've given you the central idea. Next to that central idea, I want you to write big idea. This is the big idea, the enduring understandings that are critically important. The big idea for this unit would be forces between objects cause objects to move or have a change in their motion. The concept that students are dealing with is I could use the concept of change or I could use the concept of cause and effect. In fact, in just a second, you're going to see that the next gen science standards actually use that concept, cause and effect. The vertical alignment shows you what they learned in kindergarten and shows you where they're going in second grade. Again, this is to give you the importance of why you need to teach what you're teaching. Now, if you look at the little chart below that vertical alignment piece, this is actually from the curriculum framework, and I want you to mark out enduring understandings. These bullets that are underneath what the state has called enduring understandings on that left-hand side are not enduring understandings. This is a Flanaganism that I dislike that the state does this. They are misusing terms inappropriately. An enduring understanding is the big idea. These are not. What's on the left side is what students need to know. Students need to know that objects move in a straight, circular, spinning, rotational, or back and forth motion. They need to know that a vibration is a back and forth motion, and it's a really special one because vibrations actually help to produce sound. And then students need to know that sound can make matter vibrate. And inversely, vibrating matter can create sound. That's what they need to know. The big idea is that forces between those objects can cause change in motion. Notice where it says essential knowledge and practices. Mark that out. That again is used incorrectly. Another Flanaganism. This is the do. The right-hand side is what students are expected to be able to do. They are expected to be able to make and communicate observations about the different ways objects move. They are expected to be able to write a compare and contrast between the two movements of two different objects. They are expected to be able to design a device that uses movement to transfer an object from one location to the other. So as you read these statements, you should in your mind already start to see some instructional activities that should come out of this lesson, this unit, right? So I would actually write a unit plan around these standards. one of the lessons that you're going to see is specifically on the back and forth vibrations. As you see on the screen here, I've pulled out just those two little bullets on the right, and I've pulled, you'll see in a second, some stuff on the left, and I'm going to write a lesson specifically around vibrating matter, okay? But here's the piece. When I see compare and contrast, I should think graphic organizer, graphic organizer, graphic organizer, box and T, box and T, box and T, or double bubble, double bubble, double bubble, or Venn diagram, Venn diagram, Venn diagram. It's telling me what instructional strategies I should use. Notice when I see, with guidance, plan and conduct an investigation that addresses the question, ding, 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 ding. This is an opportunity. I could use the 4-question strategy to help design an investigation. So it's telling me what my instructional activities should entail. All right, so let's look at the screen. This lesson is going to specifically be around vibration and how vibrations from an object create sound. And then we're going to look at with guidance. And I'm also going to add in, by the way, the making communication of observations and describing the relationship. I just pulled a piece of it just to kind of show you. All right, so let's walk through just what the next gen science standards say. So this is what the next gen science standards, which by the way is NGSS. So big idea. Forces between objects can cause change in motion. That's the big idea. Change is the concept. They also use cause and effect as the concept. Perfectly fine to use both. I want to teach kids an example of cause and effect in the real world, because as they're reading in language arts, they should also be able to pull cause and effect in stories, right? So if a story's about a character and this character does X, Y, and Z, what are the effects of what they're doing, right? So that's a skill that crosses all disciplines, cause and effect. So what the next gen science standards say for first grade is 1, PS, which is physical science, 4, 1, plan and conduct an investigation to provide evidence that vibrating material can make sound and that sound can make materials vibrate. That sounds very much like our standard in Virginia. So that's aligned. 1 PS4-2. Make observations to conduct an evidence-based account that objects can be seen only when illuminated. We're not doing light in this standard in Virginia, so I don't need to do that one, and it's not aligned to the state standards. Same thing with PS4-3, still dealing with light, so that is not aligned, right? Nope. And notice PS4, use tools and materials to design and build a device that uses light or sound to solve the problem of communicating over a distance. So the state standards in Virginia say to transport an object. If I was in a state that was a next gen science standard state, I could do this. But in Virginia, we're not. We're just going to use ours, which is designing an investigation or a way to transport an object over time using motion. So that's an engineering standard. So when you see that, build a device, that is an engineering standard they've tried to put in. So just when I look at the next gen science standards, in comparison to our first grade standard, there is one bullet that is aligned to what we do in Virginia. So we're not totally following the next gen, but we have some of it. So some of our standards, the point that I'm trying to make here is that some of our SOLs are aligned to the next gen science standards. We just don't do them all. We've gone rogue and we're keeping what we've always had. But you can at least see the next gen science standards. Okay. Here again is the Virginia SOL, and then you see the no's on the left-hand side and the do's on the right-hand side. Those little green leaves that you see, these are the inquiry engineering standards that they are saying, and there should be a little leaf next to plan and conduct down there, that plan and conduct investigation, because that's an inquiry piece. But here's the standard again. All right, so this is what I have, and I need to design my unit with this, right? Okay, this is going to be fun. How do I come up with a unit that's all about objects having motion and then sound? I know the perfect thing. And first graders will love it. Playground science. That's what we're going to do. We're going to incorporate and build a unit around playground science. In fact, that's what I'm going to call the unit. It's going to be called Playground Science. And I can already see how I can take them outside. We can play on the playground. They can carry their little clipboards. They can make observations. We can be playground scientists, right? So this is what's swirling in my head right now when I look at this. Again, I'm going, where in the real world do students have to use this language? Where do they see examples of straight and circular and spinning? All right. So what I've done with this chart is I've taken the no's and the do's and I've aligned them. I'm matching them up so that I have my lesson plans. If you create a chart like this, guys, and you align the things that seem to go together, it's magic. Your lessons in your unit just will fall out beautifully. So look what I've done. So I have said, I want my kids in this first lesson to know that objects may move in straight, circular, spinning, rotational, back and forth motion. And I can see that there are 2 do's that I feel like really align to this really well. Notice I didn't add the make and communicate observations of an object with rapid back and forth motion because that's really specific to vibration. So I'm going to have kids identify back and forth motion because as you're thinking about playground science, what should be popping in your head that's a great thing for kids to get on that gives them that back and forth motion? If you're thinking swings, you are right. So I'm going to have kids in this lesson, they're going to make and communicate observations about the way the different objects move. And then we're going to do a compare and contrast of 2 different objects. And maybe I let the kids pick their choice of their favorite 2 things from the playground that they can write about. So again, I'm going to give them interest-based choice, which is going to allow them to differentiate that lesson by interest. Ooh, and I can teach the process of writing, which means if they can write about what they want to write about, they're more likely to get through the writing process. Okay? So then you can see I've got this little column called activities students could do. Now, this is not my formal lesson write-up. This is just my planning document that I'm kind of throwing ideas down and I've researched stuff, right? And I'm finding activities from books and things and on the web and I'm pulling it and I'm going, does this really align? So, in thinking about this, I can sort of see this first lesson, and it may take between 2 to 5 days, depends on how I structure this. And I am hoping to give you a copy of this lesson plan so that you can see my thoughts as I kind of like develop them, but I'm not done yet. So I think on the first day to start off, we're going to go out to the playground and we're just going to have the kids play on the playground. So maybe I do this during recess because maybe recess happens before I teach science in the afternoon. So during recess, I'm going to say to the kids, I'm going to say, boys and girls, today at recess, I want you to go out and I want you to really pay attention to when you're on the swing or you're on the merry-go-round or you're on the slide, I want you to think about the motion. Okay, and so you might say, boys and girls, and you might start from the front of the room and walk to the back of the room. And you might go, boys and girls, when I walk from the front of the room to the back of the room, I'm walking in a straight line motion. I am not curving, I'm not bending, I am going from point A to point B. That's what we would describe in writing, or the word that we would use to describe that motion is straight. And then you might say, boys and girls, if I'm on a playground object that spins, and I would actually spin in place, and I'm just going spinning, spinning, spinning like a top, right? And maybe I pull out a top and I show the kids how a top spins, right, around a central point. So I'm spinning around a central point, right? That's called a rotational or spinning motion. Or maybe I choose to run around the playground. And so maybe that's where you walk around the room, right? And you're going in a circular motion. This motion would be described as circular. That's what the word means, circle, circular, right? I'm going around in a circle. And then back and forth. And you can show them maybe bending over and bending back and forth like circular, right? Or back and forth. Like I'm on the swing and I'm swinging up and then I'm swinging back and then I'm swinging. So I want you to describe what it feels like to be in that motion when you go outside. So you take them outside for their recess and in Virginia Beach, if you read the news, they have a longer time for recess. And so you're reminding them as they're on the recess and they're playing, think about the motion. How would you describe it? What does it feel like? And then during science class, you bring them in, you sit them on the carpet, and they actually have to describe how it felt to be on the swing, right? Back and forth. Oh, my stomach felt funny because it was going up and then I was going down. And as John pushed me, it was really fast and I was a little scared. And so you're writing things like, John pushed me. My stomach was weird, right? So you're writing all these things. And so this is a great way for you to introduce that vocabulary. You can then put on a video that shows that motion and they're describing it. And then in language arts the next day, you begin your writing piece, right? And you really want to make sure they understand what are some objects that go in circular straight spinning. So then you would give them examples that are different than the playground, right? So they've had experience with the playground. So maybe you give them a picture of a car driving to point A to point B, or a racetrack, right? What kind of motion would the cars be doing here? That's circular. So you give them something that's different, but it's real world. That's lesson 1. Maybe that takes, again, 2 days. It might take me 2 days to do that. Playground science, describing it in 20 minutes, watching the video. Then the next day in language arts, we're working on the writing piece. And then the next day in science, I'm introducing them to this objects move in a back and forth motion. And one kind of back and forth motion is a vibration. So we're going to actually make the kazoo when we come on Monday night because I want to show you that. So what we would do is we'd make the kazoo and they would make observations about the kazoo. And so then there's a list of questions that I would ask the students and I'll show you the activity. And then I might, the next day when we come back, right, we're explaining what is a vibration. I've got this cool video that actually shows guitar strings vibrating and you see the waves. It's really cool. And so it's a great way to talk about how sound travels in waves and they can see the waves, right? And then the third activity is we actually want to look at sound in a different way than just strings, right? Or rubber bands vibrating or a kazoo. So we're going to do this hex nut in a balloon thing where it actually makes sound. It's really cool. And from that activity, we're going to design our own investigatable question around how does sound change. So if I change the type of object, then I can get a different type of sound, right? And so then we're going to be writing about cause and effect. And the last day of the unit, which is going to take 5 days because they're going to do a performance task where they're going to have to build this object that that carries a ping pong ball across the room using motion, right? That's the unit. All from just breaking out those objectives and thinking about the lesson and finding stuff, right? And making sure that there's a tight alignment between what you're doing and what the standard is asking you to do. So again, you'll see in the lesson, sound can make matter vibrate. This is really cool. You put a speaker next to a bowl with some rice on top of it on saran wrap, and you turn the radio on, and you'll actually see the sound waves make solids move, right? You could put it next to water and you can see the ripples. So I'll show you all that. But this is the biggest piece in designing a lesson or a unit is that alignment of the framework. And then the second step would be to think about your instructional activities. What strategies do you need? And how will it look like when you lay it out? So if you are teaching next week, there's 3 groups next week. What I want you to do is pick an SOL from somewhere, grade K through 6. And I want you just to do just something like an engage and an explore that could be tied to that standard. Pick something simple, right? But you're just going to lead us through a 15 to 20 minute engage or explore activity that's tied to your standard. So when you present your lesson, I want to know what from this little piece of this 15-minute activity that you're doing, what should students what are you leading towards them knowing and what are they having to do? Okay, so I look forward to seeing those next week. And if there are any questions, let me know. If I need to come online this week, we can do a collaborate session either later, probably later Thursday night after my foundations class, or even if we want to try and meet Friday afternoon, I can certainly do that. But that is all for this piece.